All right, hi everyone. Today we are going to continue some more practice with this set theory idea and these 12 familiar sets. So today we're going to look at two things. First, the intersection and union of those 12 familiar sets, and then we're also going to prove some things about intersection and union. So let's go ahead and get started. So first we have two sets. So the set of rationals that are non-zero, and we want to see the intersection between that and the set of reals that are non-negative. So our goal in doing this is to figure out, essentially, is there a familiar set that could classify the intersection of these two sets? So when I look at this, the first thing that I want to figure out is is there anything in common with these sets at all? Could I think of a few values that are in both of these sets? And there's two things I'm going to start with. First is I'm going to note essentially the base of these. Which sets are these coming from? So we have rationals here and we have real numbers here. So again, when I think of intersection, I know that we are trying to see what's in both sets. So we know that all of the rationals are in the whole set of the reals. So if I'm looking at the intersection of these two, I know that the intersection is going to be something that's in the rationals, because that is the more restrictive of the two sets. Then I need to look at the essential power or sign that's going on up here, and I need to think, okay, so is there a value or set of values that can describe this? So looking at here, this is the non-zero rationals. So this includes everything from negative infinity to positive infinity with zero excluded. But on the set of reals over here, this includes everything from zero onward. So zero and then all of the positive values. So in this set over here, zero is not included, but everything else is included. Over here, zero and the positives are included, but not the negatives. So the only thing that these two have in common are the positive numbers. So that means that the intersection of these two sets is going to be the positive rationals. So let's do another example of intersection so that we get used to what this looks like. So we're going to do the set of all integers intersected with the set of positive reals. So looking at this here, again, Z is a more restrictive set than R. So that is going to be my starting point. And then I need to look at the sign. So here we have all of the all of the integers, so negative, zero, and positive. But over here I only have positive. So consequently, the intersection of this is going to be just the positive integers. Let's take a look at using a union. So we have the positive rationals union with the zero and positive here, so our integers, so the non-negative integers. So union's going to work a little bit differently because we are trying to include everything. So again, picture a Venn diagram here where I have set A and set B. This is going to include everything that's in either A or B. So when we're looking at this, we have to keep that in mind. So here, we want to pick the least restrictive sets and the most inclusive of the sets to try and encompass everything that is included between these two sets. So looking at this here, again, we want to start with the base. But here we want to see what is the least restrictive. So in that case, we're going to have Q as our base, the set of rationals. But here I only have just the positive rationals, so 0 is not included. But over here I have 0 included. So I need to depict having 0 and positive values. So that is just going to be Q, the non-negative rationals. So the union of these two sets is the non-negative rationals. Let's look at another example where we have the non-zero rational, or excuse me, non-zero reals union with all of the rationals. So here, again, we want to start with the base and think about what is the least restrictive set, and that's going to be R. And then I need to think, okay, so what is included in my left set? Well, these are the non-zero, so everything but 0. And then Q is everything, including 0. So the only thing that's not included in R star that is included in Q is just 0. So consequently, the only thing that I need to essentially add to this set would be 0. And then that is just actually the set of all real numbers. So we have found the union. It's just the set of all real numbers. All right, let's do one more example here where we have the non-zero integers union with the non-negative reals. So looking at this here, again, we can start with the base. So we want to think of all of the R values as our base, because this is union. And then here, 0 is included, and then all the positives, but here 0 is not included, as well as positive and negative numbers. So somehow I need to capture negative integers, but over here I don't have any negative reals. So if you're on my train of thought, the only thing that's missing here in the set of Z star is just 0. So we would have a similar situation as the previous example where I could just have R. However, this set on the left includes negative values, but the set on the right doesn't. And specifically, they're negative integers. So there's no way that I can use one of the 12 familiar sets to depict the intersection of these two sets. Because if I just leave this as R, that's including values like negative root 10. But negative root 10 is in neither Z star nor Z greater than or equal to 0. So, in conclusion, this is the intersection here is not a familiar set. So sometimes that's going to happen where the intersection actually, it does exist, they do intersect in some way, but sometimes it's just not a familiar set. So that can occur. All right, so we're going to shift gears here to some proofs of some different values. So let's look at our first proof here, where So we start with, suppose U is the universal set. We want to prove or disprove A complement is equal to A. So if you think about this in terms of logic, we show that the negation of P negation is illogically equivalent to P. So this is a similar thought. However, in order to show this, first we need to just justify it for ourselves, and then we need to do a formal proof. So just as how we would do, if in our if-then statements, we would try to see, is this even something we want to prove? Is it even true? And then we can go ahead with a formal proof. So let's just do a quick example here. So let's let the universal set be the set of 1 and 2. Let's let the set A just be the set containing 1. And let's let A complement be the set containing 2. So that means that using sort of a Venn diagram of sorts, if we have A to start, and then this is well, let me label this a little bit more clearly. The box is the universal set, and then this is the set A. So we're essentially looking at everything that's in A. If I was looking at trying to show a complement, then it would be everything outside of A. And then if I'm trying to show the complement of a complement, so the complement of this set, well, then that would just, again, get me back to A. So thinking about this in terms of actual numbers here, the complement of a complement would just give us the set containing 1. So in both of these examples here, this is shown to be true. So let's go ahead and continue with a formal proof of this. So we'll prove X is an element of A if and only if X is an element of a complement. Complement is a tautology. So thinking back to when we did logic, we used truth tables. And we can't necessarily use truth tables for just sets, but we can use truth tables for elements of sets. So looking at what this would look like here, we're not starting with propositions like we did in logic. We want to use elements of sets. So we're going to start with X being in A, and then X being in a complement, and then X being in a complement, and then the complement of that. So essentially what we're doing here is this part here is really this part here. And then the last value, our last column in our table, let me just scoot this over a little bit. Is going to be X is in A if and only if X is in a complement. So again, I only have two I don't want to say propositions because I know these aren't. Two essentially entries here, if you will. So like we did in logic, we had P and Q. So when we only, this is really only having P because we only have one set, and then this would be not P. So we would only need two values, or two rows in our table, so we just have true, false, and then false, true. So then this column here is the negation of this column. So here I would have true, false. So if we were doing logically equivalent for propositions, we would be able to stop here because we would say, well, these two statements are logically equivalent, therefore this is true. However, when we're showing that sets are equivalent, set equality, we have to show that the if-then statement is a tautology. So looking at the if-then statement, or excuse me, if and only if statement, we have to show that that's a tautology. So I'm going to focus on these two columns here. And essentially the tautology is true. So, or a tautology does exist, because for if and only if, we just have to have the same truthhood. So since we have true, true, false, false, then this is true. So we can say thus x is an element of A if and only if x is an element of A complement is a tautology. Therefore, a complement is equal to A. Done. All right, so looking at another example here, we want to prove or disprove A intersect B complement is equal to A complement intersect B complement. So right off the bat, I'm a little wary of this because if we remember from logic, this part here is one of De Morgan's laws, where we would have A prime union B prime. So I'm wary of this, but let's go ahead and just try to see, are we going to prove or disprove this by just doing an example. So let's let the universal set be 1, 2, 3, 4. Let's let A be the set containing 1 and 2, and B be the set containing 1 and 3. So A intersect B complement would be the complement of the sets 1 and 2 being intersected, which would just be 1. The intersection of these two sets here is just 1, so the complement of that, so everything in the universal set that's not 1, this would be 2, 3, and 4. The set containing 2, 3, and 4. So let's look at A complement intersect B complement. So this would be 1, 2 complements intersect 1, 3 complement. So applying the complement here, we would have 3, 4 intersects with 2, 4. And then this would just be the set containing 4. So as we can see, these two sets are not equivalent to each other. So just as how when we're trying to disprove something, we just need to find one counterexample. So you have actually, by testing this out, you have done the counterexample. So we can say, thus A and B complement is not equivalent to A complement intersect B complement, and the identity is disproven. All right, so let's do two more here. So our initial thought, or my initial thought at least, was for this problem, previous problem, was to use De Morgan's laws. So let's actually see if De Morgan's laws essentially apply to set theory as well. So we want to prove or disprove A intersect B complement is equivalent to A intersect union B, or A complement union B complement. So we're going to do this the same way that we did prior with the truth table. So here we have two sets, so we're going to need 4 rows. So just as how with set theory with logic we had, if we had 2 propositions, then we would have 2 to the second power, which would give us 4 rows. So similarly here, since we have 2 sets, we'll have 4 rows in our truth table. So first I'm going to start with x being an element of the first set, x being an element of the second set, x being an element of A complement, x being an element of B complement, x is an element of A and B, x is an element of A and B complement. I'm gonna have to continue this down below. So we have one more row that we need. So this is x, or 2 more, excuse me, 2 more columns. X is in A complement union B complement, and then x is in A complement union B complement, if and only if x is in A and B complement. Okay. So again, we only need 4 rows. So let me adjust this here. 1, 2, 3, 4. All right. So we have true, true, false, false, true, false, true, false, false, true, false, true, false, true. Oop, I did this column wrong. This should be false, false, true, true. And this column should be false, true, false, true. Then intersection here, again, this works just like and. So the only time that this would be true is if both statements are true. So we have true, false, false, false. And then the complement of this would be false, true, true, true. And then here, again, this works just like OR. So I am ORing these 2 columns together. So I have false, true, true, true. And now I just need the if and only if statement. So again, if and only if is true if they have the same truthhood. So now I'm looking at this column here and this column here. So I have false, true, 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 false, true, true, true. So that is true all around. And as you can see, I've ended with a tautology. So we have shown this statement. So So we can say thus X in A complement union B complement if and only if A is in a B complement is a tautology and then I haven't done this yet in this class, but in mathematics, when you're doing a proof, if you want to say therefore, you can just use 3 dots in a triangular fashion like that. So we can say therefore A intersect B complement is equal to A complement union B complement. Done. Okay, so we're going to do one more. Sorry, just getting myself organized here. So we have, we want to prove or disprove A and B quantity union C is equal to A and B union C. So essentially what we're trying to do here is see if we have a sort of set association going on. So if you remember the properties of mathematics, we have, let's do addition here. So a quick example of this would be 2 plus 3 plus 4. Well, clearly this is equal to 2 plus 3 plus 4. So essentially we're trying to show if we have some sort of association going on here. For some reason the word association is not sounding right, so I apologize if that is not the right word. I'm completely blanking on what it is. I do know it starts with an A, but I will get back to that if I am incorrect on that. So looking at this here, let's just try to see, is this true with just using an example of universal set. So let's have the set, the universal set be the values 1 to 8. Let's let A be the set containing 1, 2, 3, and 4. Let's let B be the set containing 1, 2, 5, and 6. And let's C be the set containing 1, 3, 5, and 7. So let's do the first one here. So A intersect B, quantity union with C. So we have the intersection of 1, the sets containing 1, 2, 3, and 4, intersect with the sets containing 1, 2, 5, and 6, union with the set containing 1, 3, 5, and 7. So let's first do this intersection here. So we have the intersection would be the sets containing 1 and 2, union with the set containing 1, 3, 5, and 7. So the final set here would just be 1, 2, 3, 5, and 7. So we're going to see, is this final set here going to be equivalent to this set here? So let's go ahead and just do A intersect the quantity B union C. So we have the set containing 1, 2, 3, and 4 intersect with the sets containing 1, 2, 5, 6, union with 1, 3, 5, 7. So let's do this union. So this would be 1, 2, 3, 5, 6, and 7. And then the intersection here, let's see all the values that they have in common. 1, 2, 3, 1, 2, 3. So it's just 1, 2, and 3. So as you can see, these two sets are not equivalent, so therefore we have just disproved this claim. All right, so that is all that I have for today. So tomorrow you will have a classwork doing examples of the things that I've just done in this video. So if you have any questions, please indicate them on the Google form, and we will meet tomorrow on Zoom to address any questions that you may have. All right, have a great day, everyone.